Um, so the most relevant announcement is, I don't think I've said this previously, probably since like day one of the class. I like to have a unilaterally imposed mid-fall break because Thanksgiving in this country is absolutely timed. It is idiotic time of year to have a harvest celebration in November. It's too late. You've missed the harvest if you put it off till the end of November. It also means that since it's also customary to have a winter break, that like the fall semester drags on without like a break, and by now everyone is probably pretty tired. And ideally, this would be like synced up. Multiple classes would have the same break, but you know, I'm just one person. This coming Friday, this class at least will not meet. So hopefully that means for you that at least that Friday morning you'll get to have a little bit extra sleep. When we start in again Monday next week, hopefully you'll be a little bit more well rested. Anyone here have an 8 a.m. class on Friday? Oh, well. I'm sorry to hear that. You'll at least have this extra hour maybe to nap after that. Anyway, with that announcement made, I won't be here on Friday at all. So I won't have my office hour on Friday. Honest to God, try not to think about this class on Friday next week. So that out of the way, let's start with the two examples that we didn't hit at the end of last period. And here are two equations that look vaguely exponential in nature. There's something that's annoying about them from the point of view of just like hitting them with a log, though. There's like addition going on. Having a plus sign inside of a log, there's no nice algebraic rule for that. But there is one other nice property about these. I think these are good problems to attack using an approach called substitution. So take a look at all the exponentials, and let's start with the one on top, 7. If you look at all of those exponentials, do they all like have a common base? Kind of. What base are you thinking of? 2. Let's use that. So this 2 to the x is just 2 to the x. Let's think about 4 to the x now. What is 4 to the x in terms of powers of 2? 2 squared to the x. So that's 2 squared to the x, which as we've seen is the same as 2 to the 2x. But that's also the same thing as 2 to the x squared. And that might seem like a silly substitution to make. Is it a true? Are all of those things true facts? Yeah, it doesn't matter which order you multiply in, so you could move that 2 past the x in that step. So let's see what happens if we make that replacement. We will now see, and I'm going to add some color coding for emphasis, 2 to the x squared plus 2 to the x minus 1 equals 0. So what am I going to do? I'm going to replace 4 to the x by 2 to the x squared. So now that we've done that, all of the x's, all of the unknowns, do they all like live inside a similar looking piece? Yeah. So something that's often a good idea is noticing, well, this is like a resultant composition. This says first take x and replace it with 2 to the x, and then do something that looks quadratic to it. Do we know how to deal with quadratic things? Yeah, let's take advantage of that. So I'm going to imagine away the 2 to the x part. That's not really a part of the problem. We'll put it back at the end. So let's substitute 2 to the x equals, give me a new variable name. y. Okay. So let's replace all the 2 to the x's with y's. We will now get y squared plus y minus 1 equals 0. Does that equation look like something we can solve? In fact, I think I don't want to do it. I want you to do it. Tell me, what is y? I hear a negative 1. Do I hear a second for negative 1? Do I hear an alternative to negative 1? How'd you get negative 1? Ah, okay, okay. Yeah, so presume like you wrote down the quadratic formula at some point. I don't think this one works out so nicely. About 0.62 and a second value also? And the other one's negative. Negatives will be a problem, but I want to write down both right now anyway. So give me the exact values in decimal approximations. Those are the 2 you said? Okay, I called the point in the wrong place. People get similar answers? All right. What were the exact values? So those are like the decimal approximations. What were the exact values? What were the things that the quadratic formula told you before you used the calculator? Negative 1 plus or minus the square root of 5/2. That agree with everyone? All right. So it looks like there are 2 of them. The 2 approximate values are apparently negative 1.62 if you do the minus choice and 0.62 if you do the plus choice. Great. Is y actually the thing we wanted to know in this problem, though? No, y was a made-up variable. I want to know what x is. So this will now become 2 separate equations. 2 to the x equals negative 1 point, well, exact values are better than decimal approximations. Negative 1 plus root 5 over 2. This is the one that's about 0.62. Or 2 to the x equals negative 1 minus root 5 over 2, which is about negative 1.62. Do both of those independently look like equations that we know how to solve? Yeah. The one on the top, how do you get x on its own starting from there? Yeah. We put it in log form instead of exponential? All right, that's the whole point of this idea of putting it into log form. X is equal to the log base 2 of negative 1 plus root 5 all over 2. And if we want a decimal approximation, we can get 1. People want a decimal approximation? I mean, I think I don't want to do it, so I'm going to stall until somebody tells me one. I think I can tell a few things already. I think it'll be negative, because I'm taking the log of something less than 1. That thing is also about a half, so I think it'll be about negative 1. but it won't quite be -1. It'll be negative point something. Neato. That agree? It certainly agrees with the intuition. How about the second one? 2 to the x equals -1 minus the square root of 5 over 2, keeping in mind that the thing on the right of that equal sign is negative. What are the solutions to that? Yeah, so now say what you said about why you don't think there should be any negatives. Is 2 to the x ever allowed to be negative? So, like, you could take log of both sides, and then, like, if you plug it into your calculator, presumably it would say there's an error, there's a negative inside a log or something. Maybe it would say, like, domain error. In fact, how many people did get, like, a calculator error? What message you get? Domain error. Okay, cool. So, a negative is not in the domain of a log. But you could tell that beforehand. 2 to the x can't be negative. So the second one has no solutions, resulting in a unique solution being that. That feel pretty okay? Let's not go through the second one all the way in the interest of time. Let's just get started on it. Let's figure out what substitution seems sensible. Do all the exponentials there seem to have the same base? Mm-hmm. What base are you thinking of? 3. This 9 to the x, I could write as 3 to the x squared plus 2 times 3 to the x minus 4 equals 0. So, what substitution should we make? 3 to the x, and let's give it a name. I guess we used y in the previous one, so why not? No pun intended. And we'll get y squared plus 2y minus 4 equals 0. That look like something we know how to solve? Descartes' law of signs says that we should get one positive solution, one negative solution. So I know the -1 isn't going to count, so it looks like this, again, has only one solution. Neato. That idea seemed pretty sensible. Groovy. So, the type of examples that I want to focus on mainly today will have much less hard algebra than what we did, and will feel much more applied. Let's talk about applications of exponentials to some approximately real-world problems. Let's talk about population growth. So, exponential functions are made to model things that grow at a rate that depends on how many of them there are. So here is one. If you have a population of things that are reproducing like living things tend to, in an environment where there's no constraint on their rate of growth, so they have all the food they could possibly eat, there are no predators eating them, there's no danger of them freezing to death or starving or anything, that population will grow exponentially until it runs into the upper limits of what its environment can actually supply. So this isn't going to be a model that will apply for all time, but for at least short periods, populations tend to grow exponentially. So let's just see one example of that. So, example. You have a population of bacteria, growing in a petri dish. If you start with a sample of 0.2 milligrams, and after 1 hour you have a sample of 0.3 milligrams, let's determine how long we should expect it to take for this population to grow to a mass of 1 milligram. Obviously, these numbers are not reasonable. I don't expect a mass of bacteria to be measurable in the milligrams, especially if it's contained in a petri dish. But this isn't a biology class, this is a math class. I don't care if the examples numbers are actually set up to be sensible. So, let's take the problem and try to apply the model to it. So there is the model I want to use in this problem for exponential growth. Any exponential function, p of t, is modeled as initial population p0 times e to the kt. E is Euler's number, k is an unknown parameter, t is time. So k is some parameter that we'll need to figure out. So let's plug some things in. In this problem, what's the initial population? 0.2. Should we include the units? Are the units all consistent? Okay, so I think if we suppress the units, we'll be okay. We just need to remember that time is measured in hours. Cool. So, 0.2 milligrams. We then measure it after some elapsed time. How long do we wait till we make another measurement? 1 hour. So at time equals 1. We have the population is 0.3. So that should be the population at time 1. So, doing that, that should be given by 0.2 times e to the k times, what am I plugging in for t? 1. Backwards, something I could use to solve for the unknown parameter k. I think so. What seems like a good set of steps? Divide by 0.2. I see the equation 0.3 is equal to 0.2 times e. K times 1 is just k, so just e to the k. There's only one unknown, it's k, and that unknown only appears once, so I can just imagine undoing everything that's done on the right-hand side in the opposite order. So first, divide both sides by 0.2. How people would use a calculator if they needed to divide 0.3 by 0.2? Well, you don't really, right? That's the same thing as 3 halves. You can play this decimal point game. So that's just 1.5 is equal to e to the k. That 1.5 is 0.3 over 0.2. All right, so e to the k is 1.5. What next? Put it into log form. What do you get when you do that? Natural log of 1.5 is equal to k. If we wanted to, we could right now get a decimal approximation. In fact, we may as well. Tell me, what is that about? 0.405. And I'll use that as like a vague sanity check. But I don't think I'll use that value for the constant, like that decimal approximation, because that would just result in introducing rounding errors in the next step. So now that we know the parameter k, let's go back to what we actually want to know. We want to know how long until we have a total of 1 milligram. So we want to know how long, so we want to solve something for t. So our goal is going to be, we know what the k is. What is k? 0.405 if you want the decimal approximation, or ln 1.5 if you want the exact thing. Plug that into this formula, t is now the unknown. So P0 was still 0.2 times e to the k we now know, ln 1.5 times unknown time t is equal to 1 milligram. And we said we were suppressing units, so let's suppress the units. That look like something we can solve by doing a lot of the same work that we just did? Groovy. What first? Or maybe I should ask instead. How do people feel confident that they could just solve that equation? Does anyone not feel confident that they can just solve that equation right now? Oh, cool. Then I'm just going to say you do. Once you have a solution, and maybe you've compared with someone near you, maybe you've pulled up a graph to look at it, and you feel confident in your answer. What do we get?
I got 3.9 years.
Yours?
Doesn't it years? Hours.
Okay, otherwise, yeah. Now I think that seems more reasonable. And that is always the danger if you like suppress units and just try to remember. If you remember the units wrong, then like you might say something silly. And you might do something like really bad. Like there's this slightly apocryphal story of the like $1 million satellite that failed to launch right because someone didn't record the units and someone measured things in like inches and someone else recorded them in centimeters, and then like the satellite blew up instead of actually launching. Don't know if that's a real story, but I hear it repeated a lot. That is like an actual thing. Okay. Okay. So keeping track of your units carefully is important. People agree with that answer? Cool. Let's do one thing to just do a quick sanity check, whether this is about right. So exponential things, what does exponentiation mean? That means you're like multiplying by the same number over and over again. So, to go from, we started a population of 0.2. At time equals 1, we got to 0.3. What did we multiply by in that time? $1.5, right? And apparently we want to go about 4 hours. So let's multiply by 1.5 3 more times. Another 1.5 will get us to what happens at t equals 2, t equals 3, t equals 4. So apparently if we take 0.2 and multiply it by 1.5 to the 4th power, we should get about 1. Let's just use that sanity check to see if that works out. .2 multiplied by 1.5 raised to the 4th. Is that about 1? Yeah. And it's a little bit bigger than, but we kind of expect it to be a little bit bigger than, because the actual time that it hits a population of 1 gram is less than 4 hours. Groovy. In fact, how many people think that if they make it to an exam or ask them to do some question like this, think they could use that to at least get the first decimal place of how long it would take? There's something to that. You won't be able to answer things exactly doing that strategy, but you can remember exponentiation means iterated multiplication. All right, feel good? So there's one model for population growth. If you have anything growing exponentially fast, use the model population is given by P0 times e to the kt, where k is an unknown constant. You should be given one fact in addition to that. You can use that to determine the constant. Once you know the constant, and you want to know something else, maybe you want to know when something happens, solve an equation. Maybe you want to know what the population is at some time, like the bottom of the page. If you wanted to know what the population is at time equals 1 day, what would you do? Plug in 24 equals t. There's no algebra in this. 0.2 times ln, nope. 0.2 times e raised to the ln of 1.5 multiplied by 24. Like something that now we could just ask a machine if we wanted a decimal approximation? Yeah. E raised to the parentheses ln of 1.5 close parentheses times 24. About 3,400 milligrams, or 3.4 grams. Yeah. And now, of course, we're getting absolutely absurd numbers. 3.4 grams of just bacteria is not sensible. Long before this point, this sample of bacteria will have eaten up all the delicious things in the petri dish and will have started just dying off. Seem okay? All right. So if you want to model what happens to a population as time really goes on, you need a different model called the logistic model for population growth, which we won't hit in this class. Here's an alternative formula to one involving the natural exponential for population growth that will work equally well. So here's the other philosophy. What's an exponential? Well, it's not just anything of the form e to the kt, although it can be. You could have the base itself be the unknown. Any exponential is given by p of t equal to initial population times some unknown base raised to the time. Do you agree that looks like an exponential? Yeah, it differs from the thing before by the change of basis formula. If you wanted to rewrite this in terms of e, you could. That's the same thing as P0 times e to the ln of b times t. So there's your unknown constant k that results in the previous formula. So we can equally well walk with this. Lambda isn't what we called it, k. So the whole point of all of that is just these two models carry the same information. You could use either one if you want to solve a population growth problem. Let's use this one to solve a population growth problem. And here it is. So let's suppose you start with a population of 3 rabbits. After 4 days, so at t equals 4, you have 8 rabbits. Oh, I fixed this typo. So after 4 days, you have 8 rabbits. Let's ask ourselves, how many rabbits do we expect to have at day 10? This seemed like something we could approach using a very similar philosophy to the previous one? I think so. So, our eventual population is 8, and this corresponds to t equals 4. So that will be this model. What's the initial population again? 3 times b, the unknown base, and I should raise it to what power? 4. That look like something we could solve for b? Yeah. Let's go through the walk. What seems like a reasonable first step if you wanted to solve that for b? Let's divide by 3. What next? Take the fourth root. And then maybe we'll worry about like plus or minus signs right now. Generally, whenever you undo a fourth power by taking a fourth root, you like lose sign information, right? This is the base of an exponential function. Are those allowed to have negative bases? Nope. So only the positive choice counts. How many people are surprised that logarithmic functions did not come into play there? Yeah, it just didn't. I wanted to know the base. The logarithm doesn't help you find the base. The logarithm would help you find the exponent, but you already knew the exponent. All right, so we figured out the base. So now we know what the model is. The model is given by p of t equals initial population p0 times b is 8 over 3 raised to the 1 over 4 raised to the t. So far, so good? Should we simplify that before we use it? Is there any simplification to do? What happens when you exponentiate and then exponentiate again? They multiply. Or I guess in this case divide, because you're multiplying by a quarter. So this is the same thing as 3 times 8 over 3 raised to the power t over 4. All right, so all of that is just setting up the model we're going to use to answer the question. What does the question now actually ask? Rabbits after 10 days. So, what should I do? Yeah, plug in 10 for what variable? T, the only variable left. So I want the population at time equals 10. Plug in time equals 10, you get 3 multiplied by 8 over 3 raised to the power 10 over 4. I guess we can simplify a little bit. That's 3 times 8 over 3 raised to the 5 over 2. Which is something anyway. That look like, well, it's already done. We just need to get a decimal approximation out of it. And the stuff underneath that isn't a perfect square or anything, so I don't think there's any simplification to be done first. Let's just get a decimal approximation. Three multiplied by 8 over 3 raised to the 5 over 2. 35-ish rabbits. Is it weird that, like, that's not a whole number? Yeah, I mean, it is kind of. Like, that tells you automatically there's something, like, approximate going on with this model. Which I guess you expect, right? The population of rabbits doesn't grow continuously. To go from 1 rabbit to 2 rabbits, there's not a moment where there's 1.5 rabbits. There's a baby rabbit at some point. So that's another thing to be worried about whenever you apply any model to a population-based thing. There's going to be some weirdness about what do these non-whole numbers mean. Like maybe you expect it to be like, well, there should be like 34 rabbits and another one about to be born. Maybe that's how you should interpret it. That's not so clear. Seem pretty okay? All right. So population growth modeled well by exponential functions. There's one last thing that grows exponentially that I want to linger on. This will be the last thing that we'll do today. And in some sense, this is like the origin of figuring things out like Euler's number. Why is Euler's number the natural exponential? It's because of what's going to happen on this page. So, let's talk about interest rates. And just like population, like I don't actually care about money. I care about this as a model of something that grows at a rate proportional to how big it is. In any period of time, you just multiply this number by something, and that's how the bank computes it. So let's do that. So let's suppose you put $5 in a bank, which has an annual interest rate of 5%, compounded once per year. Fair enough. So let's see what that would mean. There's a 5% interest rate. So in order to figure out what you have at the end of the year, well, 5% literally means 5 divided by 100. That's just what the Latin is. Why we use percent instead of saying 5/100ths is probably an interesting, like, etymological question. Etymological or entomological? One of them is words and the other one's bugs. Etymological. No bugs. So, if you want to know how much money you'll have after that one full year, multiply that by 1 plus 5%. 5 times 1.05. A lot of the computations today will need a machine. 5 times 1.05. I guess that one I probably could have just done. 5 1/4. Money sign, 5.25. I'm also always weirded out by the fact that you put like the money sign at the beginning of the number, but you say it at the end. You don't say $5.25. So I'm really bad about being consistent with that. In fact, I'm pretty sure in the homework I put the dollar sign on the wrong end of the numbers. Linguistically, anyway, yeah. It might have to do with the French. Like the words go in the other order in like French or Spanish or more Latin-y languages, right? Like adjective boss is now an autorizer. Doesn't matter. Now is not the time. Okay, so let's suppose that instead you leave it in for 2 years. To do that, you just multiply by 1.05 again. You take that same 525, you leave it in for an extra year. That 525 gets multiplied by 1.05. That's the same as multiplying by 1.05 twice. And chances are that your bank isn't going to show you the extra quarter of a penny that you want. But it presumably is in there behind the scenes in the computations they do. It should be anyway. Groovy. So if you want to know how much interest you get in an account which has an annual interest rate compounded once per year, then we know how to do it. Just multiply by the interest rate that many times. 1 plus the interest rate that many times. So, if you want to see what you get in 10 years, well, how much do you have after 10 years? About $8.14. I know it should go on the other end, but I started writing too soon. What was the exact value you used for that? No, that's just a more precise decimal approximation. What was the exact thing? Yeah, what did you ask the calculator to compute?
5 times 1.05 to the 10th power.
Yeah, nice. And maybe include the dollar sign just to make sure it's there. Cool. So, annually compounded interest rates, perfectly sensible. Now, you see a lot of times that banks will have like CDs and stuff that are advertised with an annual interest rate, but compounded like 5 times per year, or with a term that's a half year or something. Let's think about what that means. So here's what the bank's going to do. So let's suppose that instead you have the same $5 in an account with the same annual interest rate of 5%, but this time compounded quarterly, so 4 times a year, once every 3 months. Presumably not every 3 months on the dot because months aren't all the same length. So once every 365 divided by 4 days. Again, approximately, right? So what's the bank going to do? The bank is going to say, at every quarter, I'm going to update the amount of money you have. And I'm going to act as though your interest rate for this quarter is the advertised interest rate divided by 4. Which seems like a reasonable thing to do, right? I'm going to apply a quarter of the interest rate 4 times per year. So, every quarter, the bank will multiply by 1 plus a quarter of 5%. 5% is 0.05. So every quarter, the bank will multiply by 1.0125. If you trust me to have done that division correctly. So after 1 year, you need to multiply by that 4 times. So after 1 year, you have $5 multiplied by 1.0125 raised to the power of 4. And again, like that's a complicated enough number. I'm not going to try to do that by hand. It's raised to the 4th power. 5 times 1.0125 raised to the 4th power. And then I'm not going to square it again. Is that slightly more than you get with just an annually compounded interest? Yeah. It's greater by about half a cent. I guess this is approximate. Seems sensible enough? So in general, Let's do one more. If you want to put it in for 2 years, well, how many quarters go by in 2 years? 8. How'd you get 8? 4 times 2 is 8. To do that, well, again, we'll resort to a machine. Oh, I lost everything. Raised to the 8th power multiplied by 5. So again, notice, like, you have a little bit more money in the bank if it compounds more often. And in general, you wind up with the following formula. So suppose you have an initial investment of P, that's been 5 in all of the examples so far, at some interest rate R, which has been 5% so far, and you compound it n times per year, then the amount of money you'll have in this account after T years is the initial principal, then however much it's going to get multiplied by. That's 1 plus the rate over n. So the bank's going to act like the interest rate is R divided by n, because it's going to apply it n times. And then it applies it n times every year, and you wait for T years. Seem like a sensible formula? So now let's just apply that, and we'll notice something interesting happen. So, let's suppose we have a principal of $150. So 150 times interest rate of 5%, 1 plus 0.05 divided by n times per year compounded, and then we'll leave it in there for 10 years. So there's what the interest rate formula says. Let's figure out what the result of this computation will be, and then we'll go down the page. We'll increase the number of times we compound per year, and we'll notice something interesting happen. So, 150 times 1 plus 0.05 divide by 12. Now I raise that to the 12 times 10. Did I draw all those things correctly? All right, so somewhere around 247 and a nickel. I think that's enough precision for me. Let's see what happens if I adjust that for monthly compounding of interest to daily. So that means I'm going to compound 365 times a year. I'm ignoring leap years. So how do I adjust the formula to accomplish that? Replace the 12s by 365. 12 becomes 365. So I won't write. Instead, I'll just type 365. 365. About 247.2997. So let's just make some observations. Compounded more times, did the eventual amount go up? Did it go up by much? Maybe I'll do one more. Let's compound it 1,000,000 times per year. 1,000,000 just being my stand-in for a big number. So that means 365 is now going to be replaced with 1, 1, 2, 3, 4, 5, 6. 1, 1, 2, 3, 4, 5, 6. Did it go up? Did it go up by much? Let's stick another like 3 zeros in there. Let's see if we can make like the Google calculator really angry. Oh no, it's still fine. Did it go up? Not by much though. So here's the fact. As the number of times you compound goes up and up and up and up and up, it doesn't actually grow without bound. It approaches a single fixed thing. That fixed thing comes from Euler's number. If you compound like 1 billion times a year, you're basically going to get the result of exponentiating by Euler's number. And what we'll start in on next time is we'll just do like one example using that formula. We'll see we get basically this same number. Cool. All right, so as a reminder, this particular class will not meet Friday of this week. Ooh, anyone planning on maybe coming by my office hour because they want to like talk to me about that talk they went to for extra credit? Cool. I'll see you at 2. Okay. Okay. I will see you tomorrow. There's no huge rush to get it done.
We had to walk it over.